quickly getting this evil reputation that I am criticizing my distinguished colleagues to slow down, and now I had to slow down also. So we started discussing this picture doesn't mean anything. I just wanted to say I have either Navier-Stokes equation. We discussed other models, but let's say the structure is seen in Navier-Stokes equation. Or the stochastic Navier-Stokes equation, you haven't officially seen it yet. And the moment you ask various problems of maybe statistical description, control, filtering, etc., that connects to a set of infinite dimensional PDEs, a number of infinite dimensional PDEs. So this is it's a finite dimensional partial differential equation, but often you write it as an ODE in infinite dimension as a semi-linear problem. So maybe this is finite dimensional PDE or stochastic PDE, and then you have a set of infinite dimensional PDEs. Some of them are even measure valued. That signifies either the statistical description or the feedback control theory or filtering, etc. And they are, for example, like the Kolmogorov equation. You are interested in backward and forward. And then the Hamilton-Jacobi equation, you simply call the HJ, Hamilton-Jacobi equation, and this is first order. And then Hamilton-Jacobi-Bellman equation, which is actually second order, but infinite dimensional partial differential equation nevertheless. And so this comes in feedback control of deterministic Navier-Stokes equation. We will derive one of them and see today. And this comes in feedback control of stochastic Navier-Stokes equation. And subjects like H infinity control or differential games lead to Hamilton-Jacobi-Isaac equation. So this can be first order or second order, depending on whether it's a stochastic differential game or deterministic differential game. So this is Hamilton-Jacobi. Those are the words I am writing. Hamilton, and the B is for Bellman, and I is for Isaac. Isaac, 1S or 2S? 1S? This is okay in Trivandrum, nobody would know. So, Isaac is Isaac. And then if you are interested in stopping time problems, optimal stopping and things like that, what happens is instead of Hamilton-Jacobi equation, you get what is called a variational inequality. Variational inequality. So it is not a differential equation per se, but it is stated as in the form of inequality, sometimes called the obstacle problem. And then what's called an impulse control, where you only want to apply control in, it sort of echoes in a funny way. Is it okay? Apply control in random instances. Then you get a sophistication of that is called the quasi-variational inequalities. Okay, Q is for quasi. And so this picture is actually also you have it for finite dimensional ordinary differential equations, diffusions and so forth. When you want to talk about control statistical descriptions, then it leads to partial differential equations when the original problem is finite dimensional. When the original problem is infinite PDE, then these objects which naturally characterize these attributes of PDEs are infinite dimensional differential equations, and they with a long history. The Kolmogorov equation for Navier-Stokes equation with random initial data is the paper of Eberhard Hoff in 1952, and the corresponding stochastic case was derived by Eugene Novikov. He is a physicist, and I think there's an echo. Maybe it's where I placed it. Is it okay now? Now it is not picking up maybe. Yeah? And anyway, so in some sense, this is also pose a dilemma. Now you want to control the fluid flow. Hello, the director of TIFR. What is that? Dean. Well, equivalent anyway. No. The director is in Mumbai. Yeah. Yeah. Oh, yeah. But human. So only a dean is not a good. I thought dean is a good title. Anyway, so this also poses enormous computational challenge because you want to compute the feedback of fluid flow. And so we know that we need to solve one of these problems depending on which one you are talking about. But these are for it. So these are PDEs in infinite dimensions. So you need to compute the feedback. Think of I used to say that so you want to improve the control of say a hydrodynamic flow over a submarine. So you want to make the measurements. You saw that kind of formulations in Professor Raymond Stock. You want to measure in some place and apply control. So you need to if you linearize, you need to solve a Riccardi PDE. But in general, the Riccardi PDE is infinite dimensional. So depending on how vertically intense the flow field is, you may have to take very large dimensional approximation. So solving one of these, depending on the situation, is essentially at this point the theory is pointing to saying that okay, this is what you need to solve. Either you want to control the fluid, you want to give a statistical characterization. So in some sense, maybe the long-term research is devising numerical methods for this set of things, or maybe coming up with more novel ways of reducing the dimension. So reducing the dimension is the biggest challenge at this point, not only in control of fluids, but control of any complex system, whether it's filtering or control. Theoretically, we don't address this problem at this point because it's maybe not that mathematically elegant to look for reducing dimensionality and so forth. So we need to focus on that question to find elegance in mathematics. Okay, having said that, I will maybe derive one of them and show you. Starting with the deterministic Navier-Stokes equation, going to the Hamilton-Jacobi equation for a deterministic control problem and how it comes. And maybe we locally linearize that problem and get what's called a Riccardi equation. You saw that in the problem. Okay, so so far it's symbols. Professor Sundar said this looks like this Navy acronyms. So I had to put some equations. We will see this in the coming lectures. Let's start with Navier-Stokes. So I only showed you a classical form of the Navier-Stokes, which looks like this, right? Du by dt plus u dot gradient q is equal to minus p plus nu Laplace u in whatever the space, let's say in Rn. I will make it by a bounded domain later on as needed, so that we simplify the discussion. Div of u is equal to 0. So these two are in this and u of x 0 is equal to phi. This is what I formulated before. So the first step is actually to convert what is called the classical form to abstract form, because very often, why do we do that? Because it's so that we can now use the tools of functional analysis to not only do analysis at that level, but also see how these forms look like. Because remember I said that this is inspired by the similar story on finite dimensions. That is our understanding now on control and filtering and stochastic methods. And where the control? Where is the control? So how do we apply control to fluid flow, right? So the control can be on the right hand side. Control can, at least in the incompressible flow. Control can be on the boundary, or control can be on the initial data. So I will formulate the controlled problem in a moment, but let's go and discuss a few more minutes on the abstract formulation. So the abstract formulation looks like this: plus nu a of u plus b of u is equal to 0, and u of 0 is equal to phi in some Hilbert space H. So, and then we will talk about bringing in control theory. If in the abstract formulation, if the control has to appear on the right hand side, but in the classical form you are actually applying on the boundary, then there should be some form of lifting. This is also you heard in the Balakrishnan lifting discussion in Professor Raymond's talk. So I want to intensely slow down at this point and spend some time to get to these operators. And so the Stokes operator, A, is the Stokes operator. So we discussed yesterday that A solves the following steady state problem. I managed to formulate it on Rn. If you want, spatialize it, put it inside some domain Rn. Okay. And we can later make it unbounded domains and so forth. X in omega Rn, it doesn't have to be bounded domain, but unbounded you need to discuss, say, a little bit more. And u of d omega is 0. So I pointed out to you yesterday that if you define a bilinear form like this, gradient u dot gradient v dx, and also linear functional denoted this way as omega fx vx dx, right? If you define these two objects, then writing this one falls within the realm of Lax-Milgram. And therefore it defines an operator A going from V to V dash such that AU is equal to V, and A is actually isometry. Now let's go back and discuss the function space a little bit. So we define, so since it's an isometry and the Lax-Milgram immediately gives you that closed operator and so forth as demanded by the the Hilly-Yoshida, for example. So it sort of sets you up for it. But the function spaces. So there's a notion called Gelfand triple. The Gelfand triple is that what I'm going to write is an example, would look something like this. So where H, the V and H are Hilbert spaces. And this stands for the embedding is continuous. So the identity map is a continuous operator. Embedding is continuous. You know, you study in abstract functional analysis that a Hilbert space and its dual can be identified. How many studied that? Because you have this Rees representation theorem gives you one-to-one correspondence, right? And therefore, a functional, linear functional and a Hilbert space, an element in the original Hilbert space can be sort of identified. But you have to be careful when you have two spaces in mind. You cannot simultaneously identify those, and that's what is here, because once an abstract friend of mine asked me, what is all these can be identified. No, when you have H, so you pick to identify H with its dual H dash, then this embedding will force that reverse embedding, and that is this one. And that, so that is called the Gelfand triple. So in order to bring that, so that, you know, it sort of sets a platform on which we do our theory. Let's get into this. I only want to show the one connection. So you define is essentially H is like the L2 space, V is like the H1 0 space. But you have a divergence free condition here, and there's something at the normal. Remember in my lecture I pointed out that in order for a test function with this property to be orthogonal in L2 to a gradient, you only need a normal boundary condition, right? Normal to be 0. So with that in mind, let's define H as U in L2 omega. So if U in L2 omega, then the derivatives have to be obviously defined in the sense of distributions. So div of U is equal to 0 with the understanding is that this is in the sense of distribution. And also H dot, U dot n d omega is equal to 0, and this is actually H minus half d omega. That is obtained, actually it also came out in Professor Raymond's lecture. He had a space E. So the space E is functions which are L2, and also the divergence is also L2. For those functions, this normal can be defined, and they belong to H minus half on the boundary. And in that duality, you have H half. And so this makes sense. Otherwise, an L2 function, if you visualize it, it can be like steps, right? An L2 function, square integrable function, can have steps. So what do you mean by prescribing something on the boundary? Because prescribing something on the boundary and prescribing some 50 on the boundary are same. So how do you make sense out of saying something on the boundary, even the normal being 0? Why it makes sense? It shouldn't make sense, right? And it because when you put divergence either 0 or even just L2, that gives you not the full trace on the boundary, but at least the normal component to be a generalized function, h minus half. Everybody know how to talk about positive and negative spaces, derivatives? How do you talk about a fractional derivative? Fourier transform, and then you can define any derivative. And that's so you can think that's the best way to think how to take a fractional derivative. Because, so if you write a Fourier representation of a function, 1 over 2 pi n by 2 exponential minus I x dot theta u hat theta d theta, right? That's the Fourier representation of a function. Now you can write down, if it is a derivative, one derivative, what happens here? Well, you go and differentiate it. So minus I theta comes in. So you write, because there is the quickest way to understand it. This is Rn. So there is a minus I theta comes in. Right? And therefore the right hand, look at the right hand side alone. That defines the derivative of a function. Understand? Right? So, and therefore now I say, being crooked, I say I'm going to put an alpha here and an alpha here. That alpha can be a fraction, it can be a complex number too. Right? So, and then I say the right hand side now defines any derivative I want, right, of that function. Of course, then if you want to go and ask certain integrability and so forth, then this guy should help you to do that. But as far as representation, visualizing what this h minus half and what is this h half, always think of the Fourier transform, right? Agreed? Right? So because you have seen, yes or no? Okay, is agreeable? Yeah, good. Of course, then the story here is that if you have a boundary, what you do, then you need to work with this partition of unity, and there are ways to deal with domains with boundary. But immediately visualize that. The other way is to, of course, talk in terms of fractional powers or differential operators. Anyway, okay, so the h we have makes sense, and we know how to make at least the tangential velocity being 0, sorry, the normal velocity and flow being just purely tangential, makes sense within this generalized framework. So that is that h. Question.
Minus 1/2 or 1/2, h 1/2, the exponent.
Yeah, it's minus 1/2. Minus 1/2. So if you look, remember Professor Raymond's, there's a Green's formula he had, divergence formula, where he had actually u dot n and a phi, right? And the phi is actually an h1 function, and therefore its h half trace is defined. This is belongs to h half domain on the boundary. By duality, then this belongs to h minus half. So that nice framework is explained in Thiemann. So that's the reason why the space E is introduced. Those are function spaces for which the vector spaces for which the function is L2 and the divergence is also L2. Then the normal is actually can be defined as the dual of the h half space, which is h minus half. Okay. V. The space V is taken as U belong to H1 omega, such that I put this one because to say that U on the boundary is equal to 0 and div of U is equal to 0 in the sense of distribution. D dash. Okay. Why this is defined? H1 functions in multi-dimension, why those are also, maybe one dimension there can be like head functions, right? Why it is, it makes sense to set this condition. This signifies that condition. Why it makes sense? What space the boundary belongs to? Professor Raymond proved it here. The story is that if you have a function belongs to, let's say, a Sobolev space M, so U belongs to Hm on M omega, then the boundary is U of d omega belongs to H M minus half d omega. You just prove it in half space by Fourier transforms, right? You say that if it is a function and its mth derivatives are square integrable, then you evaluate it on the plane, it's trace, so its boundary, it loses its regularity, right? And so that loss of regularity is that our intuition that we are dealing with not functions that are not smooth, but now how do you make sense on the boundary? So this this makes sense as an H half valued function. Agreed? Okay. So the zero condition makes sense, right? Why this makes sense? The question. How can you say H half function, H1 functions are not smooth? Why it makes sense? Whatever you say it loud so that we can. It ends, but if it's a generalized function, right? You can define any order derivative in generalized function, right? Because if you have, let's say, du by dx, phi, test function, let's say mth order, you can always integrate by parts and write this as dm by dxm, and therefore as long as, for example, this is locally L1, the right hand side makes sense, and therefore any order derivative makes sense as a generalized function, right? So that's why this term makes sense, because we write it so easily. We'll say that the divergence is 0. Why it makes sense? Because as long as the function is integrable, any order derivative makes sense as a generalized function. It may not be smooth, it could be a delta function, it could be, right? Worse than that. Okay, so this function space, and the L2's function space, of course, this is smaller than the other one, and it is continuously embedded because of the norm is bigger than that. So it forces this situation, and therefore it's easy to show that it reverses. The duals reverse, so we get a Gelfand triple situation. So the Stokes operator actually maps. It goes from the so the Lax-Milgram actually gives you the Stokes operator going from V to V dash. Do you see that? Right? So A gives you it, the F is here, an element here, and U, the solution is an element here. The Stokes operator connects those two, right? So that's what the first shot gives you the Lax-Milgram theorem. Now, when you say what is the domain of the Stokes operator, then you have to say it more precisely. So that brings us to the regularity theorem for the Stokes operator, the Stokes problem. So Lax-Milgram theorem tells you that if the forcing in the Stokes problem, it belongs to this singular space, the solution is uniquely defined in this space. Now I give you something better. The forcing is defined in H. What space the solution is defined, right? And so we call that domain dA. It turns out that it's continuously embedded, so let's call it dA. How does dA look like? So what would dA do? if you have a forcing here in this space, is square integrable, where will the solution be? Right? So restriction of A. So that is given by the famous as a famous theorem in Navier-Stokes theory. It's called the Catabridge regularity theorem. There are other people who contributed to refinement of this, for example, in the LP version and so forth. So the Catabridge regularity theorem is that if one simple version appropriate here is that if F is now belongs to H, right, square integrable. Integrable, then U satisfies H2 omega intersection H1 intersection V. V is already all these. So this is a sort of an exact parallel to the elliptic problem. And so it gives you that. And since, so this we call dA, domain of A. And it gives you, because of the dense embedding of this into the larger spaces here, it immediately is, like I said, it sets you up for the Hilly-Yoshida theorem, for example. Okay, so that gives, this is the first regularity theorem. You can actually give more. So once you have that, the Stokes operator is very well defined. You can also define, this I let you read about, can also define fractional powers of Stokes operator A alpha for positive and negative. So intuitively, what you have in mind is, suppose you have a Fourier representation, of course you had to also sum of the generalized eigenvalues and so forth. You do have a Fourier representation, so you write it lambda I to the power alpha, phi alpha some u of phi I h norm. So this is like your A alpha u. Remember, if any u can be Fourier expanded in the eigenfunctions of the Stokes operator, and then simply multiplying by A to the power, you can define any power. Stokes operator also has other results. For example, so let me list the properties of the Stokes operator so that before we move on. So the Stokes operator, A from dA, which is defined this way, to H is self-adjoint. The fact that it is self-adjoint is because it's symmetric. Remember, I wrote a symmetric bilinear form, and it's densely defined, and therefore you have a self-adjoint, and has compact resolvent operator. So this you will immediately see. The rest is actually coming from your linear function analysis class. Has only discrete spectrum that can only accumulate at infinity, and the eigenfunctions and generalized eigenfunctions form complete orthonormal set in H. So it gives you a full picture of things. The completeness comes of course from the self-adjoint operator, but it's also the completeness theorem is known for linearized hydrodynamic operators, where it's like Professor Raymond's talk, you linearize about a steady state. But then you need to do more hard work. There are theorems of Neymark and so forth, or maybe there are theorems in Dunford and Schwartz and tracking how the resolvent decays along rays and so forth. What is this resolvent compact? You heard it a few times, right? You heard this word? Compact resolvent operator. Why it is compact? You may have studied that if it's a compact operator, the spectrum is discrete, right? It looks, behaves very much like a matrix, infinite dimensional matrix. It is compact, can be seen this way. So you define, let's say, lambda u minus au is equal to f. Another slightly different problem. So that defines, let's say, lambda I minus a, u is equal to f. Lambda is some point in the complex plane for which this is invertible, so that it belongs to the resolvent set, right? So so remember the regularity theorem, right? Where does so the regularity theorem tells you that if f belongs to domain of A, x belongs to H, u belongs to domain of A, right? Now with that in mind, notice that so what is u? U is equal to lambda I minus A inverse f. So look at this operator. It takes it maps H into domain of A continuously when lambda belongs to the resolvent set. You understand, right? So it maps it inside domain of A, but domain of A, balls in domain of A, the closure is compactly embedded in H, right, in bounded domain. And therefore, this has the property that it maps bounded sets into compact sets in H, right? So this is the reason why you have a compact resolvent, and therefore it gives you discrete spectra, and therefore the original one, this guy also has discrete spectra, but these are 1 over lambda business. So eigenvalues of this can only accumulate at the origin, eigenvalues of that can only accumulate at infinity. So this sort of finishes, at least in bounded domain, the Stokes operator as a very well understood quantity. Stokes operator and linearized problems in unbounded domain gives you continuous spectrum. So it's a more rich situation. Did I go too fast there? You understood. Take a ball. So what is so this is H, right? So the resolvent operator, I pick any point in H. So u, notice that this is u, so that is this quantity. It maps to something inside a domain of A. Let's draw it this side even though that is dense. Domain of A, right? So when F belongs to a ball in H, U belongs to a ball in domain of A, right? And since ball in domain of A is compactly embedded in H, this operator has this nice property that it starts with a ball in H and ends up with a compact ball in compact operator the set in H, right? Okay. So that's what compact embedding belongs to bounded domains. This is associated with bounded domains in these problems. It immediately gives you compact resolvent operator and discrete spectra for the original problem. Okay, so we know how to define domain of A and its fractional powers. Now let's proceed. question?
I'm not sure. The graph triple, the inversion of H dual in V. Why it isn't? It is 1-to-1.
Or why the dual is because it's linear maps, right? So you can sit down and actually try to prove that it will be 1-to-1. Yeah.
There are the dual maps of the immersion of V in H.
Yeah,
So
yeah. Okay. Essentially, by writing that inequality and taking an element in dual, you should be able to prove these results. This type of results. There's a book by J.P. O'Brien, old one. That's the best one in some sense. J.P. I may not be spelling it right. It's I forgot the title. Is one of his earlier books. It's called maybe Approximation Methods for elliptic PDE. It's one of his earlier books, not his later books are much more richer. This is the Jean-Pierre Aubin, right? One of his earlier books. It's also very good places if you want to place to look if you want to have approximations and these prolongations and extensions and all this. So he constructs duals, and he constructs, for example, the dual of H1, which so dual of H1 0 is H minus 1. Dual of H1 has boundary terms and so forth, and he does those things very well in their books, for example. Okay. Any other question? This place is okay, right?
I want to repeat it.
You want to know what is going on there? Yeah, good. So you start with the function which is only L2, right? And therefore it's inside a ball in H, right? So I need to get a chalk. We have shown that U of H2 is less than some C of F of L2, because that's what the regularity theorem gives you. Regularity theorem says that if F is co-integrable, then the solution is H2, right? Because that's what this is regularity theorem is H2. So you have this bound, and therefore if this guy is less than, let's say, some R, right? The forcing is less than some norm, L2 norm is less than some ball in R, the H2 norm will also then C times R, okay? Because that's by the regularity theorem, right? Agreed? So now come and look at here. You start with an L2 function, and when you apply the resolvent operator, right? Resolvent operator is when that part of the complex plane for which this when you go and pick this lambda, this is a bounded linear operator, right? So this is not only a bounded linear operator, but it does better. It takes you from L2 inside H2. So now your U, which is this guy, the H2 norm is bounded. So you end up showing that lambda I minus A inverse F, H2 norm is bounded, C times R. Agreed? So now, the range of this guy takes, so this operator takes points inside a ball in L2 into a ball in H2, right? But a ball in H2, its closure actually is compact in the bigger space, right? So a ball in this H2 space will be viewed as in the H topology as a compact. Its closure is compact set, and therefore this operator has this extra magical property as when you view this as an operator from H to H, it takes a ball in L2 into a compact set in L2 itself, right? Forget the dA because that's what confuses, right? The range is actually, so you're always thinking in this H. So what does this resolvent operator? It starts with the ball in L2 and gives you inside a compact set, and therefore, so that such operators are called compact operators. right? So the whole thing comes, you can see first of all the regularity theorem, and also the fact that the H2 space is compactly embedded in L2 space, right? Everybody agree? Agreed? Good. So now we can, that's a nice thing, because so that many of those properties also then carry when you linearize about another velocity field. It carries. It's just that the eigenvalues are not real anymore. They are bounded by a sector. The completeness is still valid, so many of these properties are hold. Okay. So we go back to this one to see whether we understand all operators. I will eventually put a control here. In H. So what are the operators? So A we now reasonably understand, right? It essentially carries most of the properties of the Laplace operator in bounded domain. So the operator B. So let's see how this come about and what are its properties. Operator B only brings some misery to the situation. It makes the problem more interesting because it's non-linear now, and it brings you more extra structure to the problem. So the way to understand the nonlinear operator is by introducing one more operator. Just like we were studying this one with the help of bilinear form, we will introduce a trilinear form to understand that. So define a trilinear form B dot acts on V cross V into R. Why it acts on these spaces will be evident in a moment. In the following way: B of U, V and W is equal to omega Ui d V j by dxi Wj dx. Notice that I don't like to write summations, so there's a summation over I and a summation over j. So there's an invisible hand writing a summation over I 1 to n, summation over j 1 to n, which we don't write. Why this operator is significant? Because notice that we had our nonlinearity have u dot gradient u. So often we like to multiply by W and try to visualize it like maybe some kind of linear functional acting on W. This is essentially a philosophy advocated by Eberhard Hoff in the 1951. He somehow he told us that maybe you can view this one first as a linear functional acting on V. And so since I have U, W, we just say, okay, maybe first we will understand, we just put different quantities here, U, V and W, right? And then it by simple question, then you can actually show by simple integration by parts. The advantage in using tensor is that you could manipulate like one dimension. Calculus, differential calculus, you can redistribute, and then when you get some divergence, then you apply divergence conditions. So you immediately get the property, first of all, just calculus, that B of U, VW, no good pen, B of U, that's also not a good pen. later. It's equal to minus B of U W. So that's a very simple manipulation you can do to show that if you change the role of these two, the whole thing become negative. So I'll let you show that, and you may not show it, but when you next time encounter in a more serious situation, perhaps you will. So, but you feel like showing it, try it, right? Try the other one. It's all V. Yeah. So it's all V, and so what does this mean? This also mean, what can you say about V UU? I'll pick on Coimbatore this time. Why it is 0? Yeah. So if I put, if I repeat the last two, notice that I get the minus of the same thing, and therefore this is equal to 0. This has a amazing consequence in when you try to take energy estimate for this problem, because the nonlinearity doesn't contribute to the energy estimate. The most plain energy estimate you can get, the nonlinearity doesn't contribute. But let's give some dignity to this B, right? We had to say what is this B? So first of all, I wrote this one. Why it is well defined this way, right? Because we have all these mixed derivatives here. Why should it be even defined? And why did I say, well, I try linear form, but pretending that it's maybe it has either boundedness or continuity. So let's see that and get rid of this one. And with that, notice that our quest to understand the basic structure of the Navier-Stokes would be complete once I give some meaning to this one. So we write B of U V W. So this is equal to omega Ui is even better if I, well, let's carry it. Maybe let's go to vector notation. V, and allow me to write it this way. Okay, so correct, because I have dot product here, and after doing that I have another dot product. Everybody agree with that? I just feel like writing it. What's Young's inequality? Or Holder's inequality, or somebody's inequality. So, so I want to actually Holder's inequality. So I want to apply Holder's inequality for when you have three functions you are multiplying. One of the middle one is this one, that, and that one. So the Holder's inequality will give you U, let's say L4, and gradient V is the middle one, L2, and W, L4. Okay? Why? Because 1 over 4 plus half plus 1 over 4 is equal to 1. So that is bounded by UV W. Now the simplest Sobolev embedding theorem. For omega in R2 and Rn, n is equal to 2 and 3. So Sobolev embedding theorem is that suppose you manage to get one estimate, what can you say about maybe in another Sobolev space? So Sobolev embedding theorem allows you to bound this norm by H1 And this one is easy because an H1 norm has this plus an L2 norm, and therefore you can always write this one as U of V W some C U of H1 V of H1 W of H1, right? Notice that an H1 norm U of H1 or maybe V of H1 squared contains both gradient V squared and V squared L2, and therefore you have only just gradient V, you can always bound it by H1 norm, and H1 norm also is bigger than L4 norm, and therefore all three are, and therefore this statement makes sense because V is the norm of V is essentially H1, and therefore I have shown that if I fix these two, right, notice that it appears as a continuous linear function, and therefore this is a continuous linear function in each of the arguments provided you fix the other two. Okay, so having said that, so it's a continuous linear functional. Notice that now we go back to our the nonlinearity. It is called the inertia term. When I first studied fluid mechanics, they call it the inertia term. So the inertia term is this guy. So formally, so the inertia term is that. So I'm going to write this one as some L that depends on U and V acting on W. Right? This integral formally I write some L that depends on U and V acting on W. Notice that when I fix U in V, when I fix V in also in big V, with respect to this one, because in those cases the first two are constant, so some C1 times W, H1 for all W in H1, right? So this gives the first and the crudest interpretation of the nonlinearity. So this tells you that at least to begin with, this quantity here behaves like a generalized functional, right? A generalized functional, which is a continuous linear functional acting on the space H1, right? So H1 actually on V, because it's for all space V. I have better than just H1. So what space this one belongs to? The dual space, because that's how you define the dual space. Dual space is a set of elements which are consists of the continuous linear functionals of a space. What we have managed to show is that this inertia term acts like a continuous linear functional on the space of V, and therefore the inertia term should belong to the dual space of V. So we regard, so this B of UV, let's call this one, because when you do that it also kills that gradient term. It belongs to what space? It belongs to V dash. And so then we go and write this one as an abstract entity. So this one is an abstract entity, B of UV acting on W. So this defines the inertia term as to begin with as a generalized function. It's not a good situation now, because it's now in our PDE you have du by dt plus AU plus B of U is equal to 0. Where all the terms are, we need to go and understand that, right? So if U belongs to V, if you start with, you want to see where these terms are. U belongs to V, where will this be? Where will AU be? That's the Lax-Milgram, that's how I started off. So if U belongs to V, remember I said that in the Gelfand triple you have H dash, V dash, V. If you start in here, AUV will be just right here, right? Essentially you lose, it is a Laplacian, so two derivatives get hopped. So this belongs to V dash. What we have proved here is that B of U, which is actually repeating U of U, right? U dot gradient U. also belongs to V dash if U belongs to V, correct? Right. So this operator at least is a nonlinear operator, but it maps V to V dash. It does better than that. You can actually go and do a lot better than that. But at least to begin with, this one is a nice self-adjoint operator, which we characterized. This one is a nonlinear operator. It's nonlinear. It's not linear in U. Is it linear in U? No, because it's if I put this U and U, it's not linear. It's quadratic looking functional. Even though it's a nonlinear function, it maps. So it maps V to V dash. Tell me, I have a question. It's sometimes even very mature mathematical, abstract mathematical friends ask me, if you have a nonlinear operator like that, why can't it map, be a nice person and map V to V? People who wrote many papers in mathematics sometimes ask, who haven't looked at concrete partial differential equations, right? They say, okay, you are writing a nonlinearity here, right? If I don't tell you where this thing came from, this is a linear operator. We managed to scare the person by saying that it's unbounded, so it doesn't map the space to itself, right? That one, why can't it map V to V? Yeah, let's talk about that a little bit. Question? Yeah? Yeah, so it's abstractly saying it. Yeah, but it's why it is not mapping? In some simple language. Even let's make it even simpler. Let's start with the function in L2. Forget this one for a moment. Okay? Let's start with the function U in L2. What is the most simplest nonlinearity? Okay, how about U squared? Right? Does it go inside L2? You can write it and see, right? If U is L2, then you write, if you want, you can write this as F, so it doesn't confuse. U squared, so that is finite. You want this to be a F to be L2? What do you want? You have F squared dx, and that is equal to U to the power 4 dx, and that is not finite, right? So you can immediately see the nonlinearity itself doesn't map the space to itself. So never, if you see some abstract theories where it maps to itself, then immediately rules out many of these interesting problems. What other culprit you see? When you look at this, your inertia term, what are the things which prevents you from going to the same space? What do you see when you see this guy? Maybe when you see here, there's even this song, do you see what I see? So, what do you see? What other things you see in this object, right? That prevents you from going from one space, the same space. What is it? Said something. Yeah, there's a gradient, right? So if there's a gradient, right? Now let's go and forget the nonlinearity. This you know very well. So even if you start with, let's say, h1, right? So the square, if f is equal to du by dx, then this only belongs to L2. This doesn't belong to h1. In order for this to belong to h1, you need one more derivative, right? So you have those two playing against you from going from same space to itself. So inherently, Navier-Stokes nonlinearity, it maps a nice space to not so nice space. You live with that, right? So any abstract theory you have in mind goes from the same space to itself, doesn't help here. Okay. I know we a bit slower, but I caught you in questions, so that's not so bad. Now form a, so we have, I have given some idea on these operators. we will see more of this from me and my colleagues as we proceed. So now we form a control problem, and then we discuss some more. Yep.
In that, you took that LUV. Sir, here you rub it. The functional.
I used to have a teacher, you know, whenever I will write something and you ask a question, he will raise and say, what? I didn't write anything, so that's what I did. What was the question? Yeah. Yeah. Yeah, what I did was the following. I said that let's put this whole thing as some abstract object, right? So you write this one as some abstract object. Because I don't, once I have this inequality, I don't need the specific form. So I write it as something that depends on u and v dot, of course then it will be x, times wx dx, right? So some abstract object, I know that it came from that one arrays u dot gradient u, and that's happened to satisfy this estimate and also that estimate, right? So now, as long as my u belongs to v, these two belongs to v space, they are bounded by some constants, c1 and c2, right? And therefore this quantity now acts as a linear functional. This is some generalized function here. Is even almost close to a delta function. That's what is interesting about it. So this the whole inertia term multiplied by a function, this satisfies this estimate, some c naught times w, you know, v, h1 no v, right? That's what we have here, okay? And therefore this abstract object is a continuous linear functional on the space v, right? And therefore it belongs to the dual of that, and I called, I gave this name b of uv. And so I write it as a duality pairing, so that is nothing but uv acting on space w. This is sometimes more function analysis like definition. Correct? Agreed? So this is, yeah, you take a classical form, u dot gradient, and then give an abstract meaning to it in the dual space, right? Provided these elements are taken from v. And you made it gets better if you make them smooth. Happy? Yeah. So why it is linear functional? It's linear in double G, right? I used to say that generalized functions. So they are like gods. Because you don't really see them, but you see their manifestation of their action, right? So this is Utpal knows because I say that in the class. So this one is like the manifestation of the action of this. You see u dot gradient u. I couldn't characterize because I don't have enough pointwise enough smoothness in the functions u and w. But so I characterize by the action on w. These elements from this space, right? So the whole thing is, yes, it is a linear functional on w, right? But L itself depends on u linearly and v linearly. So if I repeat it, it depends on u, bu non-linearly. That is correct. We don't have to move from here, trust me, because this is one of the best moments of this meeting, right? Agreed? Okay, so we managed to start with the Navier-Stokes equation with classical terms, but now we say, okay, well, looks like if u belongs to the space V, then these entities are at least generalized functions. That's what we managed to say. Okay, so you have that du by dt plus nu of AU. Nu is some number. For example, in a submarine, nu is about at least 10 to the power minus 8 or something. So it's very, very small in hydrodynamic examples. And so it's small, very, very small. But it's, so it's BU. And for the first easiest situation, I'm going to put a control on the right hand side.
Original equation had the pressure term. So you have to remove the pressure by.
Yeah, the projection. So that is already in the discussion. What happened to the pressure? Utpal asked. Yeah, because it's the moment you go to apply this, you are now looking in the space of V dash, the pressure is already, because I showed you yesterday that in effect you are applying the pH, but we don't have to go back to that. Yeah. Okay, because A, yeah, because A, in defining A, I had the bilinear form and so forth. We can revisit that one once again. Yeah, but it's also obtained as a bilinear form. Remember, I put it inside. So the gradient P is gone in defining that. But it's a good discussion. We are at the moment where, more subtle moment where we can go back to it as needed. Okay, so the goal is now we begin to talk about, go beyond the traditional discussions and research existed until maybe a few decades ago, where the problem is about solvability, right? At least in the in mathematics literature, it's about it's a line of thought influenced by the notion of Hadamard, existence, uniqueness, continuous dependence on initial data, right? So so that means that you apply some control, apply some boundary condition, prescribe some initial data, describe how the solution evolves in some function space. That by itself, you know, after all, the Millennium Prize problem is for just for that solvability question. So we sort of touched upon the solvability. We will go in a moment. But control, in some sense, asks the reverse question. Control theory is new to Navier-Stokes, but control research and control applications were very old, thousands of years old, in some sense, if you think about it. The type of control that occurs in the nature and so forth is so now I am going to ask some kind of reverse question. The reverse question is that let's say phi is prescribed, right? Some initial data is prescribed. Can you find a control u such that the velocity satisfies certain attributes, right? Velocity at some later time, or velocity evolution during a certain time period satisfies certain attributes. What does that mean? Let's say you have this room, you have flow field, you know, the atmospheric flow field, and then you would like to have start from the scenario at this moment, and maybe at time t you want to have a uniform distribution of velocity field, right? So you are saying something that the velocity field at a later time should satisfy something. So you are putting some conditions on the solution. The question is, can you find a u? And usually you can find more than one u. So maybe can you find a u such that the effort required in making that change is somehow minimized. That is the line of thought in optimal control theory. So let's formulate that way. The easiest one is not to prescribe a target velocity field, but say that, okay, over the course of certain period, time period, can you minimize some physical quantity, and can you find a best u? So the question is posed as follows. So find u and u such that star is satisfied star is satisfied, and let's say some integral or some norm. I usually like to write an a half norm, and you will see later on I can do a little bit more calculations there and explain why I started doing that many years ago. So plus, let's say ut in the h norm squared dt. So this goes to, let's for the moment write minimum. If you like, sometimes some calculations are easy when you write this way. So that's good enough. This was a deep enough problem to, at this point, to discuss, and I can further say a little bit more about that term. So let's see whether we understand this problem. This is sort of running reverse in ideology, philosophy, to see that this is not a forward problem now. I'm just trying to find what force would cause the particular attribute you want in the flow field, right? And saying that you not only find that u, but you find it in a way such that this entity is minimized. And so what is this? What are these two terms? And so the term 1, the first term is, let me write it maybe another way. So it is 0 to t omega u of x t squared dx dt. So that is, in its crudest form, you could see the effort required when you put this control, right? You're trying to impose the fluid, and the fluid is only forced on the right interior, and so this is the L2 norm stands for the energy. So you could say that that's the average energy in some sense. And this other term, a half norm, so exercise. So another exercise, you can write it down, and when you feel like you can do this, is that a half for u belongs to V, a half norm is equal to gradient u of L2, and it is also equal to curl of u L2. A half norm, the H norm, or the L2 norm. So, and this is fluid mechanics may not like this one, because this is, they usually attribute this to dissipation, total dissipation, and they attribute this to total rotation. This term has a name, it's called entropy. This is not one of the moments where I am making a spelling mistake. This is correct. Entropy is different.
Why do you look at L2 norm? Just L2 norm. Why you cannot?
Yeah, I'm going to tell you why. I know numerics guys, they like L2. My friend motion study also but this is, yeah, that's precisely the purpose of this discussion. So this is essentially to show this one to here an integration by parts. This one you can sort of guess this from the Lax-Milgram theorem, because Lax-Milgram theorem says that u is equal to gradient u, right? I had a V here. So all I have to do is to move a half here and a half there, right? So, understood? Think of it like a matrix. Lax-Milgram theorem established the notion of A for any function V here. So in particular I took U. Now I can move, since it's self-adjoint, every fractional power is also self-adjoint. I move that one, and then I get to the first one immediately. From here to here you need more work. Controlling fluid flow, you usually think of controlling the turbulent structure in the field. You look at the flow field and see where there are anomalous structure. That means where you have more vorticity and where less vorticity. So this is formulated in a way so that I want to minimize the total vorticity content in the flow field over the time period. That's why this. Otherwise, yeah, you could have not to just put this one. So I like this one. And there are other reasons why, because the whole Millennium Prize problem centers around if you can show that this norm is bounded for all time. So there are reasons why. But by no means I'm advocating this is what you do. And I realize that when you write down the adjoint operator, that will force an AU on the right hand side, right? So that's why numerics people don't like it. So the formulation level, we brought it to here, and all the questions I posed, whether there is, how do you know that you can find such a optimal solution, right? Can you even find, can you even tell that the class of admissible U and V control are non-trivial? Can you tell? How do you know that I can find at least one? You're thinking too much. How about how can you find that? So essentially, I am saying that, can you find a U and a big U such that this is satisfied and this is, let's say, to be finite? Can you find? Can you construct? Can you construct maybe a nice smooth function of compact support, right? Take a U with all the components C infinity, right? Compact support, or maybe 0 on the boundary, and substitute it on this side, right? That will produce a right hand side anyway, right? Because you just found any old, I don't know why I am saying old, I am old now. So any functions, old is gold. So any functions, any three functions, you form a U, right, velocity. That's a candidate to plug in here. So if I plug in here, I get something. If you go and substitute in the differential equation, I get something which is C infinity and nice, and therefore this quantity will be finite. So you can see that this is, we are not seeking an optimal pair within an empty set. The admissible set is actually non-trivial. Any other question? Okay. So how the story goes? The story goes like that. The first step, like I said in my the very beginning of my talk, that you first ask. Of course, you try to go beyond the global solvability theorem, because the solvability theorem is that given a phi in L2 and U in some class, and so that's what we can discuss. What class, the control, what should we say about this control? What is a reasonable class? What is the type of reasonable, the solution? Notice that I wrote it this way, so because it's also, you will find that when we begin to write down the solvability, it's sort of, this is what that arises, right? When I was a student, I often wondered how the function spaces arise in a fluid mechanics problem, because I understood all the fluid mechanics as being a student in aerodynamics, but all of a sudden now these people are talking about function space. It turns out that arise when you support energy equality and so forth, at least at the very the start of things. Can you look at the picture and say, what is the function space I should pick for my controls? Mind you, I am applying controls everywhere on the physical space, right? That's actually, you don't never do that, right? If you, because I have about 3 minutes to say about some interesting stories, so let's get this out of the way very quickly. And so what can you say? You want this to be finite, don't you? Right? You want that to be finite. So the class of admissible control is 0t ut h dt. Being finite is very reasonable thing to do in this the way I wrote it. So it is L to 0t h, or maybe you can write it also, if you write it this one also as an integral in that way, there. So you could have also could have written this one as L20T, L2 omega. So I formulated the problem. Now we need to ask feedback. We need to ask Pontryagin maximum principle and all those things which will come, and we'll put noise and so forth. But say when we talk about control, so this is the time I want to tell you a story. Some of the things I shouldn't say, but some of it I can say. Control of fluids, of course, comes in many problems, combustion controls and aerodynamics and hydrodynamics and so forth. But there's also, if you go and search the internet, there is something called HARP. I invite you to go and so this is called high frequency active aero heating research program. How many high frequency active auroral research program? Auroral. How many of you have heard about northern lights? What's a northern light?
So it's basically the sunlight goes there and refracts to that side due to the weather and all.
Say the Earth has a atmosphere, and then there's another layer. It's called the ionosphere. It's essentially ionized plasma. So it's all not Navier-Stokes. As you go, it's become Maxwell-Vlasov. Interestingly, so when there is coronal mass ejections or solar flares, when they come from the sun, they go and agitate the ionosphere. So you have very active instabilities in the ionosphere. You see them more when you go to close to the North Pole, Alaska, Sarah Palin's land. So you actually see this nice display of colors and so forth, because there's a lot of activity because of solar flares. The high frequency active auroral heating is in Alaska. The US government, and probably also teaming up with Europe and so forth, has a huge facility of radiators. They heat the ionosphere using high frequency radio waves. There is a massive facility. So they heat that portion of the atmosphere, ionosphere, to see whether they can stabilize ionospheric plasmas, because you know about satellites. Of course you know about satellites. You guys know more about satellites than I do. The GPS satellites, the global positioning system satellites, they're really far away. So they're outside they are in the ionosphere. So when there is solar flare disturbances, their communication is often very affected. So this program, one thing is to see whether you can heat and maybe stabilize, control the ionosphere to facilitate the GPS communications better. So there is an example of, you look very scared, as an example of the big governments actually trying to control the atmosphere. I don't know whether that's causing all these big hurricanes. Don't quote me on that. That experiment also, since government didn't say much about it outside, the tabloid writers are very angry about it. So they say that, see, one of the things that plasma does is not only the high frequency comes back, but it also sends you a lot of short wavelength, very long wavelength. So they somehow, these tabloid people managed to connect that to US government's effort to control the brains of people by. So there are books, title, you can search for this one. It's called The Angels Don't Play This Up. So there are many books on, because the tabloids and the common public are very angry that these people are, military is controlling the ionosphere by forced. So if you think putting the control on the right hand side is is not realistic. Here's an example where it is realistic. It is just in aerodynamic problems and extremely important practical problems. It is you put on the boundary, but from all along, I knew about these applications. I even worked on some of these things. So, putting a localized control is very meaningful, and so that is sort of an exotic example I give you. But to tell you that there are experiments to heat the ionosphere, and there is other things called cloud seeding. You heard about this one? How many of you heard about this? So it's you guys probably do. Know atmospheric scientists where they go and put I don't know crystals or something like that. Yeah, silver nitride.
Silver.
So on the clouds, so that they will create rain. So that's another example. Even though it's not just incompressible viscous flow, it has more other equations. But you do localize things, introduce sources, so that you can control the dynamics. And so these mathematical developments, it may look abstract to you, but it's an effort for all of us to understand and maybe contribute, throw light into these subjects. Okay, we'll see you whenever, Saturday tutorial or whatever. Thank you very much for your attention.